this question. Very powerful rollers are used to produce sheets of aluminium 8 mm thick. The force that the rollers exert on the aluminium is controlled by the amount of radioactivity that passes through the aluminium and is detected by the sensor. So you have your aluminium sheet coming in, the rollers compress it to the right thickness, and the radioactive source is above the sheet. The sensor detects how much radiation passes through, and then it goes back to control the pressure on the rollers. Okay, what type of radiation is most likely to be used in this process, and give a reason for your answer? Well, it's aluminium sheet, therefore we have to use gamma radiation, because gamma radiation is the only one that can penetrate aluminium. Alpha and beta, both of those, if the source is above the aluminium sheet, the sensor wouldn't detect them because the aluminium sheet would absorb the radiation and none of it would pass through to the sensor. So gamma radiation is the only one that can penetrate aluminium sheet, especially whenever it's 8 mm. You had 1 mark for identifying the radiation and 2 marks then for the explanation with regard to the penetration. Sources capable of producing this radiation with half-lives of 100 hours, 5 weeks and 10 years are available. Which half-life is best for this industrial process, and give a reason for your answer. Similar to the question in the 08 paper, the one I would select here is the 10 years. You get a mark for selecting the correct one. And then give a reason. It wouldn't have to be replaced as often. If you have to replace the radioactive source to control the thickness, it means stopping the machine, stripping down possibly the machine to remove the source and replace it with a new one, and then starting up the machine again. And that all takes a period of time. And as we all know, time is money in industry. So the least time the machines are turned off for, the more money the industry can make. Therefore, the best source is the 10-year one because it doesn't have to be replaced as often. Other suitable answers there identified in the mark scheme were that there's less need to recalibrate the equipment because the activity is more constant because the half-life is such a long time. But I think the best one is not having to replace it as often. Part D of this question then. Uranium, symbol U, has an atomic number of 92. One isotope of uranium has a mass number of 235. This isotope decays by emitting an alpha particle, causing the uranium nucleus to change into a nucleus of thorium. Complete the equation below which represents this decay process. Write the appropriate number in the boxes. Well, whether we know anything about uranium or thorium or not, we can work everything out because we know what an alpha particle is. It has a mass of 4 and an atomic number of 2. And looking at the atomic numbers first of all, in an equation means both sides are equal. Therefore, the atomic numbers on the right must add up to the total atomic number on the left, which is therefore 232. And working with the same principle, the total mass number on the left must equal the total mass number on the right. If it's 235 on the left, it must be 231 for thorium, which is the sum then of 231 plus the 4 for the alpha particle.